Hello and welcome to another episode of How to Understand X. Today we're going to be talking about trusses. Trusses are an engineering term for any structure of nodes and joints um, in which all these joints and nodes, they are connected and they behave as one object because of the forces that are being applied. These forces can either be compressive, so at each of these nodes, this will almost always be like a triangle. At each of these nodes, there is compressive forces, so they will be compressed into that node, or there will be forces leading away from the nodes and stretching out of the nodes. This is tension, and this is compression. And trusses are just going to be triangular connections between nodes. At least for now, we're only going to be talking about triangular connections between nodes, and trusses act as single objects. They have some kind of a pin, either on both sides or on one side, and any force, like say if you had a force on this pin, imagine there's this, if you had a push pin and a piece of paper cut into the shape of a trapezoid. Imagine you had some type of a board, right? And you had a push pin right there. And then you started rotating your piece of paper around. Since it's a single piece of paper, the entire paper will spin, and that's a pretty good representation of how trusses work. Any force that acts on a truss acts on all of the truss, and calculating each force and understanding what each force is doing, this is where truss calculations come from. Now, I'm not the biggest fan of truss calculations. In fact, I would say that I genuinely dislike them more than most things, but I can at least see how it works. Again, just to redefine everything that we need to know, trusses are structures that combine nodes and joints. We'll call them joints and nodes. And these joints are members. It might be members. I don't know. I'll just kind of switch from members to. This is definitely always going to be nodes, but we'll just be jumping from nodes to members to any type of terminology I see fit because I can't stay consistent. But trusses act as single objects. These are all connected at these nodes, so any force that acts on one of these objects will act, not on one of these objects, that acts on one of these nodes will act on the entire object. In the way that one force affects the forces that both compress or either compress or lead away, or tension, the way that the forces act on one specific node acts on the rest of the nodes in any truss. And so you can calculate what forces, what type of force is being applied, so compression or tension, and you can see that based on what kind of thing is happening. So just for some notation as well, like circles or dots at each of those triangles, those will be our nodes, and triangles at the very tip of this truss, like as we had at the trapezoid. Let's try that one more time. At this trapezoid, we had a triangle right there. That is a pin. That means that both in the x direction, so horizontal movement, and in the y direction, so vertical movement, this truss will not move at that point. There's also rollers, and we will also be working with rollers. You might see a line attached to a bunch of smaller lines like that, but essentially what these, let's say pins and rollers, these are the connections to some kind of a foundation that allow trusses to be stuck. Like, if you didn't have a pin, then again, think of that piece of paper on that poster board or whatever. If you have a piece of paper and it's not pinned to anything, and you just kind of throw it at the board, it will fall to the ground. There's nothing connecting it to anything, so it won't collapse, but Like, it won't do anything, it's useless. And so we have a pin that controls the movement in both the x, not, that's not the x and y direction. This is a pinned support. I think I call it pins plural, but it's technically the correct way of saying a pinned support. And then this is a roller support. That means that perhaps if, well, it's like an actual, like a wheel, you know? It can move horizontally, or it has, what's it called? I think tangential translation is what it's called. Oh, yeah, yeah, because if you remember calculus or any type of algebra, you might know that the tangent line is the slope right there, and the normal line is perpendicular, right? So if we kind of think of a like constant, the function like f of x is equal to like 2 or something. I know we're getting into calculus, but if f of x equals 2, then if you have a x and y axis, then y would equal 2. And on this line, each of the tangent lines will be horizontal, and each of the normal lines or perpendicular lines will be straight up. So these roller supports can prevent normal or vertical translation, but I know I'm using a lot of arrows right now. What I'm trying to say is, let me erase these two arrows right here. I'll just put circles around them to say that this is what's allowed, but roller supports only allow for that tangential movement. You can move left and right, but you cannot move up or down. It is pinned to this, well, not pinned, but it is supported by this foundation, right? It is stuck to this foundation, but you can move left to right. So you have that tangential movement, but you do not have this normal movement. You don't have this vertical movement that you, well, I mean, I was about to say that pins have, but you know, pins also have neither. Pins are just stuck in place. But again, just so that we're not like fully here, pins, well, these are both supports, that triangle and the circle. The triangle is a pin support, and the circle is a roller support. The pin support prevents tangential and normal movement. Tangential is horizontal and normal is vertical. The pin support will prevent both of these kinds of movements, while the roller support or the circle will only prevent normal movement, so only vertical movement. It can move left and right. So let's work with some simple trusses. We're going to just kind of do some examples here and there, and then we'll see where we're at after some 40 to 50 minutes, but, you know, it's honestly not too, well, I can't say it's not too difficult. I really dislike trusses, but it makes a lot more sense than you'd think it would. Like the logic in trusses, it's pretty consistent with itself, and once you see the patterns that trusses have, it becomes a lot easier. But yeah, let's work on it. Oh, and I almost forgot one last thing, or this is probably the most important thing. This is how we're going to actually calculate. I probably should have, you know, started with this, but if you have a truss, let's go back to trapezoid. If you have a truss with a pin, and you are trying to see the Fx, or the force in the horizontal direction, you want this truss to not move, right? This has to be stationary, so trusses can't move. So the forces acting horizontally must cancel out with one another so that the truss doesn't actually move. You want this to be fixed to the foundation, right? So if you can account for all the forces, then Fx, or the force in the x direction horizontally, must cancel out. So we can write this as the sum of the forces acting on x will equal 0. And it's the same in the y. We do not want this truss to either collapse or to magically start floating. So we have to account for both both the vertical directions. We say that the sum of the forces in the y direction should equal 0. We do not want it to move left or right, so we account for both the forces acting pushing the truss to the left and all the forces acting pushing the truss to the right, so that those sum up to 0. And then we focus on the forces pushing the truss up, so positive in the y direction, and then negative in the y direction, and those should cancel out. So we have the sum of the forces in the y direction and the sum of the forces in the x direction should equal 0. And lastly, I'm not sure if this will come up, it most likely will, but a moment is a measure of some object's tendency, not objects, measure of a force's tendency. So we might even say this is Fm. It's the measure of a tendency for a body to rotate about a specific point. Usually, or not usually, for our purposes, it's almost always going to be that pin. But the moment is if you have some type of a force acting upwards, let's say. It could be downwards, it could be, anywhere, right here. The force M is the force that is rotating the entire truss. So if this is, our truss so far, and this is the pin, then the force acting on this will cause it to rotate. If it wasn't, pinned by something else, it'll, rotate and continue rotating. And the force of this is force M. This is a moment of force, and the forces should cancel out. Again, we do not want this truss to start randomly spinning, so we want the force M to cancel out as well, so that we have our truss maintaining its static position, or its stable position. Static is a completely different thing that I should have also mentioned. We're going to be working with static determinant, or is it determinate? Yeah, it's a static determinant. Let me write it down. Static determinacy. Static determinacy is it's the quality of a structure that is stable, right? All of the reactive forces, all the compressive, all the tension forces, everything can be determined from equilibrium alone. As we said, f of x, the sum of these forces will equal 0, the sum of the forces in the y direction should equal 0, and then the sum of the moment forces, the forces that can rotate some truss or some object around a specific axis, which is in this case going to be our pin supports. So this rotation should be canceling out so that we don't have a spinning truss. So this is static determinacy. If this is allowed, if we have a stable truss that follows the equations of equilibrium, that is a statically determinate. I was trying to remember the term statically determinate truss. And the way to actually see if a truss is statically determinate or not, there's a very specific formula for this. So in order to determine if a truss is statically determinate or not, we need to say that 2j equals m plus 3. M plus r. And j is going to be number of joints. M will be members. And then r will be number of supports, forces, or reactions. So let's try and illustrate this correctly. Let's draw this truss that I found online. We have a pin right here and a roller joint right here, or not roller joint, roller support, and then you have this kind of a trapezoid looking thing, and let's really bubble in our joints or nodes, and we can connect them right there. So we have these nodes, and then we have one more right there. Okay, I think that's it. And of course we have nodes or joints at those points as well. And we can draw those lines. But how many joints do we have? We have 1, 2, 3, 4, 5, 6, 7. So we have 7 joints. So we can write 2 times 7 is equal to m, or number of members. So each member, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I know it looks like I'm just circling random stuff, but just every time you see a line, that will be a member. So we're going to have 2 times 7 equals 11, plus what is support reaction? Support reaction is what we've been talking about. It is the forces acting on these pins. So there is one force right there, one force right there, and then one vertical force right there. Again, rollers can move tangentially or horizontally, while pinned supports cannot move vertically nor horizontally. So we have 3 forces, or 3 support reactions, which means that we have 2 times 7 equals 11 plus 3, which means we have 14 equals 14, which means that that truss will be statically determinate, which means that we can actually calculate the forces acting on this truss with the force formulas that we were given. Okay, now let's work on some examples. I think that's everything we need to know. If something random comes up, then I'll probably have to address that. But I think that's most likely going to be it. We'll see. Okay, let's see. I will start with something relatively easy. So let's start with a nice and simple triangle truss. Let's say we have a triangle. Let's let this be, I'm not sure if this will be isosceles or not, but we have this triangle right there with a height of 5, and then each of these are 5. There's a pin support right there, a roller support right here, and a 100 Newton force right there. So at this pin support, we have a force in the x direction. So we'll say this is, let's actually, let's label all of our joints. We have A, B, C. So we have F. Okay, come on. This is a little bit annoying. FAX, not fax. We'll put that subscript. Yeah, we'll say FAX. And then we have a force acting in the y direction at A, so F, A, Y. And then we have a force acting solely in the vertical direction, so F, C, Y. Okay? And let's try and calculate everything. What do we know? We have, let's see if this is statically determinate or not. We have 1, 2, 3, 4, 5, 2 times 5, number of, whoops, sorry, no. We have 1, oh, we have, I can use the correct thing. Okay. We have 1, 2, 3, like joints. So 2 times 3, and then we have 3 support forces, right? FAX, FAY, and FCY. So 3, and then this is actually not a member. This is just a angle, or not an angle. This is just a measurement to show you the altitude. This is not an actual part of the triangle. So there's only going to be 3 of these members. So we're going to have 3 plus 3, which is true. This is a statically determined truss, so we are able to, do stuff with it. So because 2 plus 3 is equal to 3 times 3. And so now let's try and calculate. So let's write down everything that we know. We know that F, the forces in the x direction, the sum of the forces in the x direction should equal 0. The sum of the forces in the y direction should equal 0. And the sum of the moment forces should equal 0 as well. Okay? If we try to sum up the forces in the x direction, there's only going to be one force in the x direction, that is FAX. So FAX plus, if there was something, oh, that should be a capital A if we're keeping our notation constant, FAX, if, there was another force, then we would add it, and then, something equals 0. But since there is only one force in the x direction, and the sum of our forces must equal 0 because this is a statically determinate truss, we have the only force in the x direction, FAX, will equal 0. Okay? That was pretty easy, right? We just saw that we need to sum up all of our forces to equal 0 because we determined that this is a statically determinate truss, and we only have one force in that direction. So now we need to calculate. Oh, wait, did I write FM? I mean, I'm not sure if that's like bad notation or anything, but we're only going to be calculating the moment around our pinned support, so moment about A. And so how would we calculate a moment? I probably should have mentioned this one as well. A moment is calculated by distance times force. If you're trying to calculate the force that you are like rotating something about some type of a pin or axis, then like imagine if you have a single like very small stick, you would not need as much force to rotate it, but the longer the stick, the higher the proportion of force is necessary to keep it moving at the same kind of rate. But yeah, distance times force is how we are going to be calculating moments. So this will be distance from the pin, right? Both horizontal and vertical distance, because we have to care about that. So what is the horizontal distance from the pin of FAX? Well, that will be 0, right? Because the pin is at the pin. The position of the force will be at 0 because we are rotating it about that pin. So we'll have 0 FAX. And then now we have a force acting in the vertical direction, right, at that pin. So where's the how far is it away from the pin? It is on the pin, so there's no distance there as well. So we have 0 FAY. But this isn't only going to be 0. There are multiple forces acting on this truss. There is a FCY, rotating it like that. Let's kind of try and draw how this would look like if you could just let it rotate. You can follow that kind of a curve, and this 100 is pushing it on that axis, right? So there are two forces that are not of 0 distance from here. So we're going to have 0 FAX plus 0 times FAY. And so let's start with this 100. This is 100 newtons. This 100 Newton force is coming downwards, right? So you can think of it as it's moving negative in the up direction, or you could just think of it as it's moving downwards, because, all of our other forces are pushing upwards on this truss to see the moment about A. So you can think of it as moving plus negative 100, or just negative 100 times the distance, which is 5. If we're keeping this same, we have distance times force, so we'll have negative 5 times 100. And then lastly, plus, because we're still moving up, plus 10, we have 5 plus 5, 10 times FCY. And that's going to equal 0, right? The sum of the forces of the moments about A should equal 0. Now these two are, they don't have any values because they're multiplied by 0. So we're going to have negative 5,000 here, plus 10 FCY is equal to 0. So 10 FCY shall equal 5,000 when you add 5,000 to both sides, which means that FCY will just be 50 newtons, right? 5,000 divided by 10. And yeah, I think that makes sense. Like, if you just kind of think of how this is like moving, if you put a bunch of pressure at the very base of some triangle, the support is already, supported by the foundation. So the forces acting up on it should, cancel out at some point, which is where we get to how we get FAY. The sum of the forces in the y direction should also equal 0. So we have FAY, that's acting in the positive y direction, plus FCY, again, positive y direction, minus 100 equals 0. So if we have FCY equals 50, 50 minus 100 is 50, so we have FAY, not 5AY, FAY should equal, should equal 50, right? When you have 50 minus 100, you get negative 50, and then you add 50 to both sides. So you get FAY is equal to 50 newtons. That makes sense. You want this force to cancel out this force because you want this truss to stay in the same place. FAX will equal 0 because we're not actually moving. And I'm not sure if I actually mentioned this, but these are ideal trusses. The horizontal movement in a real truss in real life, where there's wind and all sorts of factors affecting how trusses move and exist, in real life, those roller supports will not be completely static. You will have some FAX that is not equal to 0. You'll have something acting on this truss from different directions, different places, and forces will be unequal. But we are working with statically determinate trusses in like this ideal truss length. So we're already, very limiting as to what is possible. So we have to follow the rules of equilibrium, which is, the sum of the forces in the x and y direction and moments, they should all equal 0. So I'm hoping you saw those processes. We have to determine if the truss was statically determinate, and then we simply just listed as many forces as we could find on every support, and then try to keep our supports on the sums of our forces equal to 0, and then we just did some basic algebra. But let's do one or two more slightly difficult ones, and then we'll talk about compression and tension and try and see where compression and tension kind of lies. Okay, this is a slightly more advanced looking one. We have a trapezoid, like we started with, trapezoid like that, with a pin right there, a roller right there, and this is 2 feet. 2 feet. This is 4 feet. So I'll draw that over here, 4 feet. There is also 500 pounds being like forced onto that one joint. There is also another 500 pounds being attached to the, not attached, but done to that one point. So let's label these. We have, starting from right, then going down, we have A, B, C, and then D, E, and I think that's essentially, oh, and we also say that this is 2 feet long. That's going to be important. And there's also a diagonal going through like that. Okay. So we have 2 times 5. That's A, B, C, and D, E. So we have 5 joints. And then we have one vertical force right there, and then one vertical, and then one horizontal. So 3 forces right there. Then we have 1, 2, 3, 4, 5, 6, 7. 7 members for this truss, which means we have 2 times 5 is equal to 7 plus 3, or 2j is equal to m plus r, which means that we have 10 is equal to 10, which is true. This is a statically determinate truss, so we can actually start calculating some of these forces. And in some classes, you might be asked to, solve for these angles and, the exact compression themselves. I think we might talk about that in a little bit, but right now, I just want you to see these trusses and how forces work on these trusses. I think that's probably a little bit more important than calculating tension and compression, because this is a little bit more basic, and this is a little bit more necessary to fully understanding what's even happening on these trusses. Okay, so let's first work on the moments. I think that might be perhaps the most difficult. So let's say that this is going to be f dy, f e y, and then I'm switching from lowercase to capital, but f dy, f e y, and then f e x or something. Again, I can't stay consistent, but this is 4 feet, and now let's try and sum up the moments. So the moment forces about any point should equal 0, not just at that pin. So, mi is just, placeholder. So we have the sum of the forces about me. That should be relatively easy, because the force Fe, x, will not have anything. It'll be multiplied by 0. So we will have 4. That's the distance. Let's call moment A. This moment right here. This is 4 in distance times 500, which is that force. And it is moving counterclockwise, so this will be positive. And then this will be plus another 500. At that C, so this isn't moment A, this will be moment E, this is moment A, and then moment C, this distance between those two is going to be 2 feet as well, because this is a square, so we'll have 2 times 500, and then from here we'll have minus the force dy, because this one's actually traveling counterclockwise, right? If all these other forces are traveling, not counterclockwise, this will be traveling clockwise, f dy will be traveling clockwise, and all the other forces are traveling counterclockwise. So this is negative f dy times, this is 2 feet right there, 2 feet. So we're going to have 2 times there, okay? And so we can, solve for this. This should equal 0. At the end of this, we're going to have 0 is equal to 2,000 plus 1,000 minus f dy times 2. So we're going to have 3,000. So we can add that 2 fdi to the other side. 2 fdy is equal to 3,000, which means that fdy is just going to be equal to 1,500 pounds. Okay, and now we can start calculating fey, right? That's the other vertical force. And let's see. I'm not sure. This graph is getting a little bit cluttered, but I don't think there's another force acting on this, or another vertical force acting on it other than Fey. So if Fdy is equal to 1,500, we can say that Fdy, or well, let's write in 1500 now. 1500, okay. 1500 plus FDY, or FEY, is equal to 0, which means that if you subtract 1500 from both sides, then you have FEY is equal to negative 1500. That does not mean that there is a negative force being pushed on. You can think of it like that, but it's probably a little bit better to think of it as just the force is going in the opposite direction. If there is a 500 or 1500 pound force pushing upwards, then there has to be a 1500 pound force pushing downwards to keep the truss stable. So we know what FEY is. Now we simply need to calculate FEX, and we should be good. We will talk about compression in just a second. FEX. Now, this one's going to be relatively normal, I'd say. We have, 500 plus 500 plus FEX will equal 0, which means that FEX will equal negative 1000. Right, when you add 500 and 500, you get 1000, you bring that to the other side, you'll get negative 1000. Again, that's not a negative force being pushed on it, that is just a force pushing in the opposite direction. We have FEX will look like that. And this is negative 1000 pounds. Okay, now we can start talking about how to calculate angles. Angles and trusses are also very important. If you have a, say, 1 degree truss, then it'll definitely act in a much more different way than a, say, 45 degree or like a 30 or 60, some of the more normal truss angles. So you want your trusses to be relatively stable, so they can't just have crazy looking angles. So let's continue working with this one. We have this trapezoidal truss with a roller right there, pin right there, A, B, C, D, E, and then 1 right there. So 2, 2, and then we said all of that was 4. So how would we calculate the angle of, say, BED? BED. Well, we are given 2 values. We don't know the hypotenuse, even though we could calculate it. We do know 2 legs. We know the side opposite of BED, so that's just going to be 2. Well, don't want to say exactly what we're doing, but we know that the side opposite of BED, that angle is 2, and then the side directly adjacent to BED is going to be 2 as well, which means that opposite over adjacent, or tan, BED will equal 2 over 2, or 1. And now if you did arctan on both sides equals arctan of 1. Well, the arctan and tan cancel out. Those are 2 inverse operations. So you're left with the actual measure of BED. And that is arctan of 1, which some of our Traeger fans might know would be 45 degrees, or pi over 4 radians. So we're going to keep it 45 degrees. So this will be 45, and this is a square, which means that these angles are 90 degrees, which means this is 45, and by complementary angles, this is also 45, 45. This is a right triangle as well. I needed some help thinking about that, and this is 2, and because this is 2, this is a square, right? And if this is 2, then this has to be 2, which means that this is also going to be 45, and 45. So yeah, that's kind of interesting. It might be useful, might not be. But at the very least, we know how to calculate. We need to use tan or sine or cosine, whichever operation you're capable of using, just to isolate that variable. And then we can use vertical angles, complementary angles, supplementary angles, and just do whatever you can to make some kind of a formula that looks familiar to us, right? Some kind of a x plus y equals 90, or x plus y equals 180, or x equals x if you have that vertical angle, Do whatever you can as long as it looks correct. And now let's briefly go over compression and tension. We did very quickly mention that at the beginning, but we do need to kind of understand what it is. Okay, so let's draw a truss really quickly. We have, let's assume that this is statically determinant, because, we could probably come up with some position of rollers and stuff, but I don't think that's strictly necessary. We simply want to see which forces are compressive and which forces are tension. So we have this triangle goes over here. That was a nice triangle, by the way. And then we have a force that goes here. So W will be our force. Then we go A, B, and then these members are Q, R, so P, Q, R, and then S, and then we have some type of a foundation right here, right? So those lines just indicate that there's a foundation, and now let's try and see which of these forces are going to be tensile or compressive. So we have 4 members, right? P, R, Q, and S. The forces are acting on the nodes, but the actual force itself, it exists within the member. So the only 4 things that have compressive or tensile forces in this diagram of some 7 or so letters, the only 4 things are P, Q, R, and S. The members are what have the the ones that have the forces. And the way to see what tension looks like is by kind of trying to imagine what a shape would look like without some side. So imagine we didn't have this S member, right? So we're just left with this, this should probably actually be a pin. Let's just imagine we have this triangle, and then this force pushing it to the right. This triangle will simply rotate along this pin. It'll rotate about that point, and it'll follow this kind of a curved pattern. And point B, right there, point B will be moving towards this wall or floor or whatever. Point B is moving towards that, which means that S is in compression, right? There is a force from B acting on the S, pushing inwards on S, and we see that like a compression. Or you can even think of it as a, if you are trying to draw it with respect to the, with respect to the node, then, or to the joint, then there is a force being applied from S to B as a B, moves away, or something. I'm trying to think how to explain this. So I mean, I would rather just show them with respect to the member itself, but there is a way to demonstrate this with respect to the actual joints. That I'm forgetting kind of how to explain why it works, but it does work. I'll put a video down below of some example of somebody using it with respect to the beams, and it made a lot of sense when he was doing it. So, yeah, this B, if you just imagine that S didn't exist, B is pushing inwards on S. There's a compression happening on S, right? And if you just continue applying similar like things to the other members, like say there was not a say there wasn't a R, right? So we'll try and draw this. Say there wasn't an R, we have this kind of a structure. A moves down, right? A moves like down, it's falling down, and or actually, let me not explain it like that. Let me explain how compression and tension like affects one another. The end of R connected to B is experiencing a diagonal force upwards from S, right? S is like pushed inwards, so B is going to be pushed outwards. This is probably where that like explanation of force on the beam probably works a little bit better. But this compressive force on S then results in a tensile force on R. The as B pushes inward on on S. Let me try and draw this. As B pushes inwards on S, R is being stretched outwards, right? As S is being, quote unquote, crushed, R is being stretched. So this is a tensile force as S is being compressed. And P and Q have a somewhat similar relationship. If you think of the member P is exerting some kind of a force on F of A, then P is actually being stretched as this force W pulls on this entire truss. P, if you kind of like think of this as like a rubber band almost, and let's try and draw a rubber band right there around that node, and let's say that you have a like pin or something right there. As you pull the entire pin, well, you don't even have to pull the pin that far, just pull it straight right, you will be having a tensile force if there is a force acting on A. And I know this truss isn't like drawn the best. There could be a force acting on on the actual foundation, in which case this truss will be, not this truss, this member P will be under compression. But if we are assuming that it does, act on A, then if you just thought of a rubber band that's connected to A, P would be stretching. This would be under a tensile force. And then Q, it's a similar kind of thing. Just imagine if you like knocked out Q, you just have this like formless blob almost. It's a very weak quadrilateral, and as you pull on this whole structure, it's starting to crack and bend, but it's going to be pushing Q, this imaginary Q, further from where it originally was. This is a tension force as well. So, yeah, it's a little bit confusing. I will do most likely another video on trusses, and I'll be talking about how to calculate compression and how to calculate tensile forces, and we'll find more examples and see more of these videos. I did find a very nice demonstration of tensile and compressive forces just by seeing how, like, it's that same, knocking down a member, and then seeing how this like truss would move if it reacted to forces normally. You just kind of continue along that path, and it was really interesting. I thought it was well illustrated. Everything was good, but yeah, I'll definitely probably put that in the description. But I'm hoping you see some of the like basic ideas behind trusses. Essentially, trusses are, for our purposes, we are working with ideal trusses that are most likely statically determinate. That means they have an equal number of twice the number of joints and members plus support reactions, and you should be able to see that trusses, which are just structures that move as one, they react to certain forces, external forces, in opposing ways. So each force must be canceled out. This is kind of like Newton's laws, but each force has an equal and opposite, not every action has an equal or opposite reaction, but this is kind of like forces of that law, every force in the x direction must have a opposite force in the x direction as well. Every force in the y direction must have an opposite force in the y direction. So you want these forces to cancel out because you want this truss to be stable. You don't want it spinning or moving or doing whatever. You want it to be stable. So you want these forces to all cancel out, and that's how we do that. Moment, again, is just distance times force, so that's pretty easy to remember. But I think those are probably the most important main ideas out of all of this. That's how you calculate these forces. Angles, you just have to use your trigonometric properties: opposite over adjacent, sine over opposite over hypotenuse sine, adjacent over hypotenuse is cosine. And depending on what you're given, you will probably have to calculate different kinds of angles, but I didn't spend too much time on that because I thought it was relatively, okay. I'll probably do another video on this, explaining in further detail, angles, how to calculate compressive and tensive forces, or tensile forces, and, just in general, it's really not too bad in my opinion. I think that trusses, well, we didn't get to the worst part of trusses. Trusses get significantly more annoying. But trusses, I feel like they make sense, but you have to think in a very different way than you're probably used to. So, you have to visualize instead of actually just kind of do, which is it doesn't usually work for me. It didn't work for me when I was doing trusses, but I hope it works for you, and I hope this video, helped you. If you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And as for my music recommendation, I don't know, honestly. I've been listening to way too much Reggie. That Traffic track, it was just so good. Since this was a bit of a shorter video, I'm gonna stick to a relative classic at this point, and that is the beautiful Dragon Ball Do-Rag. This song is hilarious. It's good, it's funny, it's well performed by Thundercat. Bass is obviously fantastic, genuinely, enjoyable. And, the lyrics are obviously somewhat stupid, but I think that's the point. I think it's definitely the point. But it works well, it stands up on its own as an actual expression. And on that merit, I have to respect it. But it's kind of stupid. It's very funny, though, especially the music video. It's hilarious. But, most of Thundercat's discography, it oscillates between, ridiculously good, and then him perhaps deliberately holding himself back from his true potential as an artist, which it's a little bit disappointing to see, but most of the time he does pull through. He does have incredibly enjoyable tracks, and the Dragon Ball Do-Rag is definitely up there. It's one of the best songs in his discography, in my opinion, which is saying quite a bit. He has some genuine classics under his belt. He's worked with Kendrick Lamar. He's worked with quite a few famous people, but he is very good on his own. Listen to his bass. He's very good at playing the bass. And Dragon Ball Do-Rag was a great track. I like it. I listen to it quite a bit. And if you like it, please comment down below. But yeah, I think that will be it. Now I just need to come up with an exercise, and then we'll be good. Um, let's just say, how about everybody watching this video does some air bikes. Air bikes are a good exercise. I was doing air bikes the other day. They are quite painful the day after, but they're fun. So, yeah, do some air bikes, and bye.